Today we study X25Q. You can download the PDF file for this lecture from our K-pop digital library. You can visit kpop.org, kpope.org, and in the table of contents, so you can click X series to scroll down to find X25 Kinetic Theory of Ideal Gas. The main textbook can be found in here, and then we have checkpoints, multiple problems, and NQ, that is for the preparation of Q, and we have dispersion Q that has X25Q, kinetic theory of ideal gas. In each PDF file, you can click this to find a Korean lecture and English lecture. And then if you click this to return to the K-pop digital library, and then if you have not subscribed to YouTube channel of K-pop, please click this to visit the K-pop collaboration homepage, the YouTube homepage, and subscribe. Okay, so let's begin with the X25Q kinetic theory of ideal gas. Number one, describe a brief history of the kinetic theory of ideal gas. So first of all, we consider Boyle's law. It was found and published in 1662 at temperature T with a fixed number of molecules. The product of pressure and volume is preserved. Second, in 1738, Daniel Bernoulli is famous for the Bernoulli's equation, developed a theoretical approach to reproduce Boyle's law based on the molecular level. So it is a simple application of Newton's law. And Bernoulli family has many famous people, and Jacob Bernoulli is the person famous for the introduction of the limit of the Euler number in 1683. So in 1773, Lavoisier introduced the principle of conservation of mass. Dalton introduced in 1802 the law of partial pressure, in which the pressure of a mixed gas is sum of the pressures contained in a single container. In addition to Boyle's law, there is another law called Charles' law. It is also an empirical law that if the pressure is invariant, then the ratio of volume and temperature is a constant. We have Avogadro's law, and let's read it through. Who proposed the empirical law in 1811. The volume of a gas of an equal number of molecules at the same temperature and pressure is the same. And in 2019, the new SI definition appeared. The Avogadro's number is exactly defined as this number. It is an exact number. In 1859, Maxwell introduced the first statistical law of nature, that is a Maxwell distribution. In 1871, Ludwig Boltzmann introduced the Maxwell-Boltzmann distribution. 1905, Albert Einstein published a paper, Brownian motion, regarding the diffusion of molecules. 1906, Ludwig Boltzmann introduced the entropy formula. So we will work on the problem later. We consider the ideal gas equation in related to the kinetic energy of molecules. Kinetic energy of a single molecule. So this symbol represents the average over n identical molecules. The kinetic energy of a molecule can be computed in three parts, introducing Cartesian coordinates. If we neglect the gravity, then due to the isotropy of the Euclidean space, these three contributions must be identical to each other. Therefore, the simple calculation can be made by a single uh, average over the n identical molecules for a single component, a single Cartesian component contribution to the kinetic energy. One can compute the pressure on a wall by assuming that each collision is elastic. A molecule's velocity along the x-axis can be flipped into minus to keep the kinetic energy the same before and after the collision of the molecule against the wall. As a result, the momentum transfer to the wall by a single molecule must be twice the linear momentum of each molecule along that normal direction. Because it returns to the same wall after traveling by twice of h length, we divide it by the speed along the x-axis. Because the force applied to the wall is a pressure, not a pressure, the momentum transfer divided by period. So we have this formula, this delta P divided by this. So factor of 2 cancels, and we have the L in the denominator, and velocity is squared. Using these results, we can compute the pressure applied, exerted on the wall, that is the average force divided by the area multiplied by the number of molecules. Because we have x1 squared is just 1/3 of x vector dot squared, so we finally have this kind of relation. Sure, L cube is replaced with the volume of this cube. This one results in the relation, so 1/2 mv squared, this average kinetic energy of a single molecule, is 3 PV over 2N. Now we make use of equipartition theorem that all these contributions are the same due to the isotropy of space. So we replace them into KBT. The final result is PV equals NKBT. So this ideal gas equation PV equals NKBT is obtained. So next we consider a mixture of two kinds of molecules, N1 identical molecules of each mass M1, and two identical molecules of each mass M2, a mixed, and its temperature is T and is the container size is a capital V. Okay, so each molecule specifies the PV equals NKBT, and 1, 1, 2, 2 are used. Because KBT is identical to each other because they are in thermal equilibrium at the same temperature, we can use the KBT equals 1/3 of M1 X1 vector that squared. And this does not mean the Cartesian coordinate, but the identifier for the type 1 and type 2 molecules. All right, because this is 3 times x1 dot squared, something like that. This is x1 dot, this is a vector dot squared, and this is a Cartesian component x, Cartesian component y, or z. So that is to be replaced with KBT, mass times a single Cartesian component velocity squared average. So finally, the pressure is the sum of the partial pressures, and each pressure can be computed n kBT over V, n2 kBT over V. So we add them up to find the total number n, number of molecules. This satisfies the system, the mixture of the gas. So this one is the simple explanation for the law of partial pressure by John Dalton. That's it for today. Thank you.